Hello everyone, welcome to the TIFR CAM Colloquium. Here I would like to introduce our own Venky Krishnan, who will be telling us about momentum ray transforms and an application to a Calderon-type inverse problem involving polyharmonic operators. Over to you, Venky.
Yeah, thank you, Nishant. Before I begin, so thank you for coming. So this is based on joint works, actually a couple of works, one with Sombuddha Bhattacharyya and Suman Sahoo, and the other with Ramesh Manna, Suman Sahoo, and Vladimir Sharafutdinov. So I'm actually going to follow a different order from what I actually put in the abstract. So in the abstract, I put that I'm going to first do momentum rate transforms and then do Calderon inverse problem, but I'm going to switch the order. And then I'll see, so the momentum rate transforms actually comes in the latter part of the talk. And so Nishant, you can hear me clearly, right?
I can hear you clearly.
Okay. So I thank Nishant and Ujjwal Kole for the very kind invitation to give a talk at the TIFR CAM Colloquium. Okay, so we will start with the Calderon inverse problem. So this is actually a very, by now a very classical problem. But because this is also a colloquium, so I thought, the first few minutes, for people who are not familiar with this, would actually get to know what this problem is about. So the basic problem is the following, that so what Calderon asks is that by making steady state voltage and current measurements at the boundary of a medium, can one actually recover the conductivity of the medium? And so in mathematical terms, it boils down to this particular problem. So where this gamma here is the conductivity, and gamma, so for well-postedness, we actually assume that it's bounded below by a positive constant. You can also relax that assumption. That leads to this notion of cloaking and things like that, but which I'm not going to get into. And so what Calderon asked is, so suppose you are given this this measurement operator. So you put the potential F, and then you measure the outgoing current flux, which is going to be given by gamma du du. So you don't know gamma, but what you have is you have this gamma du du at the boundary, and then you put a different voltage, and then you measure. You can physically measure this gamma du du, and then you can repeat this as many times as you wish. And from this, the question is, can you actually recover the conductivity gamma? So so this is what is called as the Dirichlet-Neumann map, or voltage to current map. And so one thing to notice is that this is a very hard problem for the following reason, that this is actually, you're asking for an inversion. See that this PD is linear, right? But you're asking for an inversion of a nonlinear map, because as you change gamma, there is no reason to believe that your n gamma changes in a linear fashion, right? So once you fix gamma, then it's a linear problem. So what you're asking is an inversion of this nonlinear map, gamma going to n gamma. Okay, so as is usual, if you cannot solve the nonlinear problem, then you try to solve the linearized problem. So what Calderon did is to linearize the problem near constant conductivities. And so this is actually, so before I do this, so this here is a boundary operator. So it takes boundary values to boundary values, but it's advantageous to actually look at what is, so this particular operator Q gamma, which is called as the power required to maintain a certain potential, whatever. So and these two are equivalent information. So you know n gamma, then you can find Q gamma by integration by parts. So you will actually look at the inversion of this map, gamma going to Q gamma, where Q gamma is now given over. So the advantage here is that it's given over the integral over the whole domain omega. Okay, so as I said, so instead of looking at this inversion of this nonlinear map, what Calderon did is he linearized the problem near constant conductivities. Or in other words, you can, without loss of generality, you can take it to be gamma is equal to 1, and then he considers the pressure derivative of this operator. Okay, and this is not difficult to check, that the pressure derivative linearized near constant conductivities is given by the first, the linearized map BQ gamma. Okay, and now it's a linear problem, and the reason why you have that U is harmonic is because you have linearized near constant conductivities. If you linearize your other conductivities, then depending on what conductivity that you choose, of course the form will change. But because we have linearized near constant conductivities.
Venky,
yes.
Sorry to interrupt you, but at least to me the voice trails off in parts. So sometimes it's right there, I can hear you properly, but occasionally it trails off a little bit. I don't know if the other audience members also feel the same. So
yeah, so I think I should not move around. I will just stick to my position over here.
I think that will be very helpful.
Yeah. Okay. So so as I mentioned, because we have linearized near constant conductivities, so we are looking for so we have this U to be harmonic. Now the question is, now you can specify the Dirichlet data, any Dirichlet data that you want, right? And now it's a linearized problem. So now the question is whether if I assume that this is equal to 0 for all U harmonic, because why all U harmonic? Because you can specify what Dirichlet data that you prescribe on the boundary. So this F is under your in your control. Okay. So then the question is, can you show that at least the perturbation is 0? In other words, this delta here is 0. Okay. Now by polarization, so it's more advantageous to look at, instead of this here, to look at this part. In other words, you are allowed to have two different harmonic functions, right? That's because you just consider U1 plus U2, U1 minus U2, you get the same thing. Okay, so you have this equation. It's an integral identity, and the question is, you specify U1 and U2 harmonic, right? Can you show that delta is equal to 0? Can you show that delta is equal to 0? Now, although I'm not going to get into this, now you can ask a lot of other problems. One is that if you have a partial data problem, right, then you are allowed to have. So here you have no specification on what your Dirichlet data is. But what you can now ask is, if you only have that F is going to be supported on a part of the boundary, then you need to produce enough harmonic functions which are only supported on a part of the boundary to actually show that this identity is equal to 0, implies the perturbation is 0. So these are linearized Calderon, which are quite hard. So the linearized problems near with other restrictions. But I'm not going to get into that. So the question is, are there enough harmonic functions U1 and U2 such that this product here is dense in some sense? Okay, and what Calderon showed is that the answer is yes. And so let me just repeat the problem. So what we have is, so we have this identity is equal to 0, and you are allowed to prescribe what U1 and U2 harmonic that you want. Okay, so you specify the harmonic functions, and then can you show that this delta here is 0? Okay, and the answer is quite simple, surprisingly. So you take this particular harmonic function, U is equal to e to the I x dot zeta. Well, not all zeta is going to satisfy that this is going to be harmonic. You just double differentiate, sum it up. Then this is going to be harmonic if and only if the zeta dot zeta is equal to 0. But let me just remind you that this zeta dot zeta is not the dot product, right? It is just as a vector. So this complex vector multiplied by the complex vector and then summed it up, that's going to be equal to 0. Okay, what it means is that the length of the real part should be the same as the length of the imaginary part, and the real part and the imaginary part should be perpendicular to each other, because the perpendicular part is what comes with the I. The length of the real part and the equal to the length of the imaginary part is what comes as the real part of it. Okay, because zeta dot zeta is not real. It's going to be complex vector. It's going to be a complex number. Okay, so now what we need to do is, what Calderon did is to show that you can produce this enough of this harmonic function so that when you multiply gradient U1 with gradient U2, dot with gradient U2, you get e to the I x dot c. Okay, why? Because then you have recovered the Fourier transform of delta, and that if you show it is equal to 0, then by Fourier inversion you have the delta is equal to 0. Okay, there is this part over here, this mod c square vector, but that's not an issue. Okay, so you produce enough harmonic functions such that this condition is satisfied. And why this? You can do it in all dimensions bigger than or equal to 2. Okay, because later on I'm going to show you that you can only do it for dimensions greater than or equal to 3 using this approach. But here you can do it for all dimensions bigger than or equal to 2. So you choose zeta 1 to be equal to this, and you choose zeta 2 to be equal to this. Now you must have that the length of the real part is the same as the length of the imaginary part. That's what is the condition over here. And the real part and the imaginary part should be perpendicular to each other. That's what the condition over here. So now when you take gradient and multiply and things like that, because the C here is a fixed frequency, you specify the frequency. So you end up with the Fourier transform multiplied by a polynomial. So therefore you have that, assuming some regularity on the perturbation, you have that delta is equal to 0 almost every. So Calderon showed that the linearized problem is true. Okay. So now the invertibility of the nonlinear map. So the nonlinear map, remember, was to show the invertibility of gamma going to n gamma, right? So this invertibility of this nonlinear map was taken up by Sylvester and Ullman in their fundamental paper, right? And what they did is they produced this the notion of this complex geometric optics solutions in contrast to the real geometric optics that comes up in hyperbolic involving hyperbolic PDEs. Okay, so what is it that they did? Okay, so first step, and this is the fundamental step in many of these problems, is to reduce the problem to a lower order perturbation of the Laplacian. And Laplacian is actually going to be quite crucial for our purposes because even to this day, we don't know how to deal with the general operator. Okay, so we can transform the problem, the conductivity equation, which was this equation, to this equation. Okay, where this Q is actually quite special. Actually, I have given the transformation. So you do this particular transformation, differentiate it, put it back into the equation, to this conductivity equation, and then V will satisfy this particular problem. And this Q here is actually quite special. It's going to be the Laplacian of square root of gamma by square root of gamma. And gamma is bounded below by a positive constant, so there is no issue. So one thing to emphasize is that gamma is at least C2. So you assume that gamma is at least C2, and which is the assumption that Sylvester and Ullman made in their paper, in Analysis of Matter. Okay, so now what you have is the conductivity equation. So now the original problem is as follows: that you have the Dirichlet-Neumann map corresponding to the conductivity equation. Now from that we have transformed the problem to what is called as a Schrodinger equation, which is minus Laplace plus QV is equal to 0, right? And because V is related to U by just multiplying by gamma to the minus half, we can expect that you must know at least some information about gamma to begin with. The information that you need to know about gamma to begin with is that gamma should be determined at the boundary, right? So this is due to a paper of Kohn, actually two papers of Kohn and Vogelius, that you can actually, from the Dirichlet-Neumann map, you can actually recover all the derivatives. Assume gamma is, let's say, C infinity. You can recover all the derivatives of gamma at the boundary. Okay, and so using that, so now what we have is you have transformed the problem from involving study of the conductivity equation to the Schrodinger equation. And so I have not given what the relation between the Dirichlet-Neumann map corresponding to the conductivity equation with the Dirichlet-Neumann map for the Schrodinger equation, but it's believable, right? Because you have this gamma to the minus half, you just need to compute that. Okay, it involves one derivative of gamma. Okay, so the question is, so now we will just study only this problem. So you have this conductivity equation, you can specify whatever Dirichlet data that you want, and you make the Neumann measurements, right? And the question is, so the Neumann measurement here is going to be just the normal derivative, du du. Sorry, dv du. Okay, I have used v here over here. So dv du. The question is, can you determine q? And once you determine q, then because q is related to gamma through that a PDE essentially, right? Because it's Laplace root gamma by root gamma, you can actually recover gamma from that particular equation. Okay, so we're not going to focus on that. I'm just going to focus on this particular problem in which my it's important that So what I want to recover is actually in the form of a lower order perturbation of a constant coefficient operator, in this case the Laplacian. Okay, so what the ansatz that Silvester and Ullmann propose is the following. So they look for a solution of this form. And why this form? Because so for the case of the conductivity equation, which the linearized near constant conductivities, Calderon looked for solution which were of the form e to the I x dot zeta. But now what we have is you have a lower order perturbation of the Laplacian. So you don't want harmonic functions now. You want solutions to the Schrodinger equation. And because it's in the perturbation is in the lowest order, this will not work for if you have a highest order perturbation. That is perturbation in the Laplacian. This strategy will not work. Okay. So then you look for solution of this particular form, e to the I x dot zeta times some a. You can actually take this a to be equal to 1, but I will fix this. I will take it in the form a. I will explain that in just a second. And plus r, which is a remainder term. So now now you plug this back into the equation, and you have freedom in choosing a. So I choose a such that this condition is satisfied. For a is equal to 1, it automatically is satisfied. But it's good to have a little bit flexibility. So this is what we call as a transport equation. So this so for this transport equation, I try to find solutions involving a. Okay. Now I can choose a to be something of the form e to the I x dot c, where c is such that c dot the real part of zeta, c dot the imaginary part of zeta, that's going to be equal to 0. That would be a solution. Okay. So now, what about R? R is very, very important. Actually, the majority of their paper is actually establishing this R, but not just this R. R with good decay properties at infinity. Okay, so they do it by a different method, but now there is a very powerful method using Carleman estimates, because you look for this conjugated operator. Okay, so you can actually establish the existence of this R. Not only that R, you can also establish the existence of R with this decay. Actually, I don't need this decay for the purposes of this talk. This decay is good enough for me. Sorry, the bound on the gradient is not required for me. The bound on the decay of R is important. Okay, so existence of such solutions are what we call as the complex geometric optic solutions. So now let us just plug it back in, see how we actually solve the problem. Okay, so now remember in the Calderon, the original linearized Calderon problem that Calderon considered. So you had u1 dot u2 is equal to 0 for all u1 u2 harmonic. This is what we had, and then we wanted to show that does it imply delta is equal to 0. So now, because you are considering a lower order perturbation of the Laplacian, you will actually end up with the following integral identity. Integral q v1 v2 is equal to 0 for all solutions v1. So v1 so q is the difference, q1 minus q2. Okay, actually that particular identity is very easy to derive. We just use integration by parts. So here I'm using the fact that the Dirichlet data are the same, the Nyman data are also the same. So therefore, such type of boundary contributions will not appear. Okay, so therefore, when you plug it back in, you will actually get an integral identity of this particular form. Integral q v1 v2 is equal to 0, where v1 is a solution corresponding to minus Laplace plus q1, v2 is a solution corresponding to minus Laplace plus q2, q is a difference. So now all that we need to do is to produce enough solutions v1 and v2 which solve the Schrodinger equation such that the product approximates e to the I x dot c. In other words, the product is dense in certain sense. Okay, so I'm just going to show that the product v1 and v2 are close in certain sense to e to the I x dot c, and that can be done. And this is where the dimensionality is important. So the fact that the dimensions n bigger than or equal to 3 plays a role here in actually able to produce enough solutions v1 and v2 which approximates e to the I x dot c. And because you have this v1 and v2, when you plug it back in, see my v1 is of this form, right? My v2 also of this form. So now you see that you will have terms involving r1, r2, r1 and r2 only. So those terms have to vanish, as zeta gets large. That's why this decay condition is important. Okay, so when you plug it back into this particular equation. Okay, so in other words, I only need to consider, because of those decay condition, I only need to consider the highest, the so-called highest order term, or the term involving the solution to the first transport equation. So the reason why I'm mentioning this is because we are going to do this in the more complicated setup of polyharmonic operators, where the first transport equation, solution to the first transport equation is going to what is going to play the essential role. Okay, so now what we have is, so we want to produce this so that this is close to e to the I x dot c. And so actually the proof in n dimensions, at least this approach, in n bigger than or equal to 3 is the approach that was taken by Sylvester and Ullman. And okay, so I don't want to get too much into this. I have explained the idea. So you choose the solution V1 in this particular form. You choose V2 in this particular form. So now the place where the dimensionality comes is in choosing these three vectors, which are mutually perpendicular to each other. Okay, so that's where the dimensionality comes. Now, then what you have is you would have recovered the Fourier transform of the difference, which is equal to 0. Therefore, Q is equal to 0. Done. Okay. Now the proof also works, not the proof. The theorem also works in 2 dimensions. But remember that in 2 dimensions, the problem is significantly harder because it's a formally determined inverse problem. In dimensions 3 and higher, it's an overdetermined problem. So therefore, in dimensions 3 and higher, this approach works. It does not work in 2 dimensions. 2 dimensions was an entirely different approach. And it was also a paper in the Annals of Math by Adrian Nutt. I'm not going to get into that. So this one is only n bigger than or equal to 3. Okay. So now I want to get into an yes. Yeah. So the question was the Carleman. So you are asking about the Carleman estimate, right?
I'm asking about that. Is the existence a consequence of the Carleman?
Yes, exactly.
So it allows us to give the right question.
Yes, exactly. And also the decay. It also gives the decay. It also gives the decay. Both are required.
Because the tau or the base comes in front of.
Exactly. Okay. So the question was about the I don't know if the people joining remotely were able to hear. So the question was about the Carleman estimate. So the Carleman estimate is required to have the decay also. So the decay property also. Okay. So now the Calderon-type. So before I get into the polyharmonic operator, I want to deal with other type of Calderon inverse problem. And this is actually it opens up a whole lot of other possibilities. Even today, there are so many open problems in this field. But let's consider one such, which is what we call as a magnetic Schrodinger, in which we consider also a first order perturbation. Okay, the first order perturbation is given over here. W is a vector field now. So now the question is, from this Dirichlet-Neumann map, which comes from integration by parts. So can you recover W as well as Q? Both these. Okay, that's the question. And so W cannot be determined completely, right? So W cannot be determined completely, and that's because what we call as a gauge invariance. So the gauge invariance can be seen as follows: that you take any CC infinity function in omega, then you take its gradient, then you change the magnetic term, sorry, the vector field term by W plus grad phi. Okay, so then for the W prime, you let the solution be V, and you can actually check that the solution is going to be of the form U e to the minus I phi. And because phi is CC infinity on the phi is CC infinity on omega, the Dirichlet values are not changed. And you can also check that the Neumann values are also not changed, right? Because Neumann W plus grad phi, but grad phi is equal to 0 on the boundary. So the Neumann data is also not changed. So the implication is that from the Dirichlet-Neumann map, you cannot recover the magnetic term or the vector field term. Okay. so you can recover the potential term, but you can recover only a component of W, the vector field, the curl. Okay, so there is so in the Hodge decomposition, the curl of that. So you cannot recover the entire vector field. Okay, so there is a gauge invariant. So you see that. So this is again a lower order perturbation in effect, right? Because when you expand this out, it's going to have minus Laplace plus a first order term plus a zeroth order term involving mod W squared Q and things like that. So therefore, the question is, can you also recover all these terms? Right? The answer is no. You can only recover a component of W, and Q can be recovered if you write it in this particular. Okay. So now the other type of problems that I want to consider, and I already briefly mentioned about this in the linearized Calderon setup, are the partial data problems. So from a physical point of view, the entire boundary is not accessible. So you only may have accessible to part of the boundary, or you can only make Dirichlet prescribed on a part of the boundary, or you can only make Nyman measurements on a part of the boundary, and still you want to see if you can actually solve uniqueness questions. And this has been done. This was initiated by a paper of Buchheim and Ullmann, where they actually introduced Carleman estimates in the context of elliptic inverse problems for the first time. Prior to this, it was known in the formally determined hyperbolic inverse problems, which now goes by the name of the Buchheim-Klebanov method. But it was introduced, the same Buchheim. So the Buchheim and Ullmann, they actually introduced elliptic in the context of elliptic inverse problems, Carleman estimates to actually solve the partial data inverse problem for the first time. Okay, and this was significantly improved by this paper by Koenig, Sjöstrand, and Ullmann, which actually came out in 2005. It was another annals paper. Okay, so what they introduce is the following. So if you observe in the ansatz that I proposed to solve the Calderon problem, it was e to the I x dot zeta. So it's actually linear. It's a linear weight, what we call as the linear weight. So they introduced nonlinear weights for the first time, which we call as the limiting Carleman weights. The limiting Carleman weights. Okay, and so what is this limiting Carleman weight? So linear weights are one example of limiting Carleman weight, but there can also be nonlinear weights. One such example is given by this half log of mod of x minus x naught the square, where x naught is a point on the exterior of omega, or exterior of the convex cell of omega. So the limiting Carleman weight is given by this. So okay, I have not introduced this, but this h here we can think of it as 1 over mod zeta. So h is a small parameter, so there you let mod zeta go to infinity. That's the same as considering this h to go to 0. And so if you look at the principal symbol of this conjugated Laplacian, or the conjugated semi-classical Laplacian, so the real part is going to be given by this. The imaginary part is going to be given, okay, 2 times gradient phi dot c. And the limiting Carleman weight is that this Poisson bracket is equal to 0 when this is equal to 0 and this is equal to 0. Notice that there is a close connection to what I just said earlier. The length of the real part should be the same as the length of the imaginary part, and the real part dot the imaginary part is equal to 0. So there is a connection. Okay, so this, I'm not going to get into this. So we are actually going to use a very specific limiting Carleman weight. Actually, we're going to consider the linear weight. But for the case of Calderon problem with partial data, you have to deal with nonlinear weights. Okay, so now let's come to kind of focus of this talk. So one can actually consider now higher order perturbations of the higher order or higher powers of the Laplacian. So one such thing is to consider minus Laplacian power m, where m is at least 2. Okay, so now what you can do is you can consider lower order perturbations of that. Okay, so this was studied by Krupchik, classes, and Ullmann sometime in early the previous decade. And what they did is they considered this first order term, and then they considered this 0th order term. And so now it's a m is it's a polyharmonic operator. When m is equal to 2, it's a biharmonic operator. So you can specify the following Dirichlet-Nyman map. And the question is, from this Dirichlet-Nyman map, can you recover both A and Q? Remember, when M was equal to 1, okay, at least in the setup that I just mentioned, there was a gauging variance. But now when M is at least 2, the gauge disappears. Okay, so one can actually recover both A and Q completely. Okay, so this is a result due to Krupchik classes endowment, and again in dimensions n bigger than or equal to 3, because it's again based on the CTO technique. Okay, and yeah, so there is one thing that I want to mention over here. So one can either work with this Dirichlet-Neumann data, or one can can consider this what is called as this Navier boundary conditions. So you specify U and Laplace U on the boundary, and then you take the normal derivative of U and the normal derivative of Laplace U. So you can also make this partial. Okay, so the partial in the following sense: partial in the sense that the Neumann data is specified on a part of the boundary. So I haven't quite specified what F sharp is. Just think of F sharp as an open subset of the boundary. But really, F sharp is specified. It is an open neighborhood of a shadow. Okay, but we don't need to worry about that. So just consider this F sharp as a part of the boundary. But I just want to emphasize that I am not imposing any restriction on the Dirichlet data. So you can ask a question whether even if I specify some support condition on the Dirichlet, right, and I measure Neumann, the Neumann measurements only on a part of the boundary, can I still specify? Can I still uniquely determine both A and B? That problem is still open. Okay. Now, what has been done is the case in which you have a magnetic Schrodinger equation, right? And in that magnetic Schrodinger equation, you can specify support of U on a part of the boundary, and you can take Neumann measurements on, roughly speaking, a complement of the support of the Dirichlet data, and there you have uniqueness result. But this was actually quite a difficult proof. It was proved by a former student of Carlos Koenig, so for the magnetic Schrodinger. But we tried this, but we were not successful, or we are not successful yet to actually do this for higher order operators. But we have not been successful. The main difficulty is the following. The main difficulty. You have a question?
So in the real analytic case, this is the original for the question.
Correct.
So
Yes.
you need to say that in the class of smooth.
Exactly. Right.
It's not so.
Yes. Exactly.
But the real partial data problem is okay.
Correct. So the real, so if you consider only C2 conductivities or even smooth conductivities, the smooth coefficients, the problem is still open. And the difficulty here is the following: is that so the way it was done is, in order to produce solutions with that R, the remainder term with proper decay at infinity, you need to actually, so the Carleman estimate is in positive Sobolev spaces. But what you need to do is you need to shift the index so that you can use a Hahn-Banach type argument to show the existence of this R with prescribed regularity. So what you want is, you want H1 solutions if you are working with partial Dirichlet on for the magnetic Schrodinger, right? And the difficulty is in shifting the index. So now, if you also specify the Dirichlet to be on a part of the boundary, then you have to produce solutions U which are H1 on a part of the boundary, right? And sorry, H1 0. That is, it is 0 on a part of the boundary, and that's where the difficulty comes. So the primary difficulty is shifting the index. Shifting the index to the left, right? Because the Carleman estimates will give you like an H1 L2 Carleman estimate. But what you need to do now is to shift the index to the left. So on the left you have L2, on the right you have H minus 1. But this is also on a part of the boundary. If there is no support restriction, then this shifting in the index is quite easy. You can do using a pseudo differential conjugation operator technique. But at each stage you have to specify that on a part of the boundary, it's only supported on a part of the boundary. So that is where the principal difficulty comes. And the difficulty here comes because now I need to have higher regular solutions, at least H2, right? And at least H2 solutions, but H2 which are also 0 on a part of the boundary. So that's a primary difficulty here. Okay. So again, to emphasize, again to emphasize that this support is free. There is no restriction on the support, but this I can make some support restrictions. And so I'm not going to get into this. So for this case, if you consider the usual Dirichlet-Neumann, then you can only put partial data on the highest order, and this is because of a restriction of the method. It's because the Carleman estimate comes from an iteration argument. That is, you first prove it for the Laplacian, and then you iterate that to actually produce for higher order, higher powers. So again, that is a restriction of the method. So for instance, this is taken still on the whole boundary. So it's also an interesting question whether you can specify this on a part of the boundary. Okay. So now a generalization of Kupchi classes and Ullmann's result. So I will go through this quickly. Is that you can actually consider several lower order perturbations of the Laplace of the polyharmonic operator. So this was a result due to Tuhin Bosch and me few years ago. So we can also, from the Dirichlet-Neumann map, we can recover all A, all BK, and all Q. Okay, so I will not get into this. So this was a result about 8 years ago. Okay, so now what about other perturbations, other type of perturbations? So far you see that here in the previous in this particular setup for powers of the Laplacian, lower order powers of the Laplacian, this was isotropic. Okay, this was isotropic, and this is also of a very special form. And you can ask the question.
Okay, we can see your screen. Now your screen is back. Yeah.
Yeah, sorry about that. Yes. So now you can ask, what about other perturbations? So what we call as anisotropic
Your screen is gone again.
Yes.
Now we can see it, and now it's gone again. You know what the problem is? Because I can hear you.
Yeah. So no, because okay, ultimately what you want is, so this was with regard to a partial data question. So when you shift the yeah. So I'm just repeating the question. The question was about whether you have uniqueness issues when you shift the index to the left. That's a question, right? So okay, the problem boils down to the following, right? So what you have is you have integral q u1 u2 is equal to 0, where u1 and u2 are solutions. But now u1 and u2 are solutions with 0 on a part of the boundary. So you still need to produce enough of these solutions so that the product is dense in L1, right? Now, but in the higher order case, that is when you consider the magnetic Schrodinger, you also need u1 and u2 to be at least h1. So h1 and also 0 on a part of the boundary. So that the fact that you can produce this h1 comes from shifting the Carleman estimates, the index in the Carleman estimate to the left. And for the case of partial data, what you need to do is you actually use a heat flow. But for the general case, you can use a pseudo differential operator technique. So there is no issue with regard to Peli-Wiener that I don't think so. Yeah.
Because the zero information is always there.
Yes, exactly. Yes, that's the point. Okay. So what about anisotropic perturbation? So this was two generalizations were considered. One by actually both by Sombuddha and Tuhin, former students of TIFR. So in the first part, they considered this matrix perturbation AJK, but with m bigger than or equal to 3. And then they actually relaxed this condition with this AJK, again a matrix perturbation, but with m is equal to 2. And what we want to do is we want to consider a further generalization of this one. Okay. So the generalization that we consider is the following. So you have minus Laplacian to the m, and you have an anisotropic perturbation of this kind, where all these A, M, these are all tensors or tensor fields, which are symmetric in all its indices. And then you have this lower order perturbation or the zeroth order perturbation Q of x. And the question is, from a corresponding Dirichlet-Neumann map, can you recover all this Q and all these AM minus, all those tensor fields. And we just want to emphasize that the technique that we introduced here is substantially different from earlier works. And so that leads to the notion of momentum rate transfer. Okay, now for our methods to work, we actually do a partial data problem. So for our methods to work, we actually need to assume some kind of isotropy on the highest order term. So this highest order term corresponding to here with j is equal to 0, I need to assume at least one isotropy. Okay, so that the isotropy is indicated by this Kronecker delta. Okay, so we don't need to worry about that, but for our methods to work, we actually need to assume this. Okay, so the question is from a Dirichlet-Neumann map. So we actually consider the Navier boundary conditions that you specify u Laplace u up to certain powers, and then you take its normal derivatives, du, d nu, d of Laplace u, d nu, etc., all the way up to certain power, that m minus 1. The question is, from a partial data, can you actually recover all the tensor fields and all the zeroth order term q of x? So we actually consider linear weight in this problem, and so by the choice of a linear weight, our problem actually boils down to is essentially a slice by slice reconstruction. Okay, so the problem boils down to a cylinder. The problem boils down to consideration on a cylinder. Okay, so let me just get to the theorem. The theorem is that from the Dirichlet-Neumann maps, which are given by these corresponding to the two different coefficients, we can recover all the perturbations and the zeroth order terms. Okay, so as with the previous case, we actually propose an ansatz of this particular form, but now because we have the higher powers, so we need to consider several lower order perturbations, but all these come with certain powers of h. So as I mentioned, only this part plays a crucial role. Okay, now the advantage here is the following, that the slice by slice reconstruction comes from consideration of this x1 comma r comma theta, because my Carleman weight is essentially of the form x1. Okay, so it's e power some x1, so or ix1, something like that. So that x1 is what plays a role over here, and that's what I have indicated in this figure. Okay. So what we have is, so we have an ansatz of this particular form, but I'm only going to focus on this particular case. All other terms, including this r, can be handled. So r, the decay of r, and as well as several of its derivatives come from the Carleman estimate. Okay, so there is no issue about that. And because I'm not prescribing any support restrictions on the Dirichlet, the shifting the index is not a problem. Okay, now this A naught here satisfies the following transport equation, which is given here as follows. And my phi here, as I told you, is it's of the form, it's x1. So that is my Carleman weight, and my psi here, which is going to be in the base space, and I'm going to choose my psi to be equal to r. Okay, so I use polar coordinates on the base space, one dimension less space on the base space. And now what I'm going to do is I'm going to do a slice by slice reconstruction, essentially on that perpendicular part, perpendicular to x. Okay, so now the advantage here is the following, that because m is bigger than or equal to 1, m is bigger than or equal to 2, you have a lot more freedom in choosing this A naught. Actually, that is what actually helps in showing that there is no gauge invariance for polyharmonic operators when you consider lower order perturbations, because you have freedom in choosing your A naught. Okay, so let's see. So the general solution to this particular equation is actually of this particular form, and my z here is x1 plus IR. My z bar is x1 minus IR. So my z minus z bar is going to be some 2i something r raised to some power. So that r is what is the momentum part that I want to explain. So the general solution to this particular transport equation is of this kind. Okay. So now let us see. So now in our case we have a more complicated integral identity. So in the previous case, in the case of the Calderon inverse problem, it was just Q U1 U2 is equal to 0, where U1 and U2 are solutions to the Schrodinger equation. So now, because we consider tensor perturbations, so you have such type of it's a complicated integral identity, and you have freedom in choosing this A and this B, and you choose enough of this A and B so that you can recover all of this and all of this and of course this. That's what we want. So we want to produce enough solutions A and B such that this is satisfied. And in this case, the momentum rate transform appears naturally. So we will see why. Okay. So when you plug it back, so when you plug the solution, the CGO solutions A and B, which I have given it over here. Where is it? Here. So when I just plug it back in and then let this H go to 0, and I essentially end up with something like this. Something like this. Okay. So I'm skipping a few steps, but what I want to do is, so this W here is the difference of the tensors corresponding to the m-1th level. And the important part to notice is that there is this R to the alpha minus 1. So this R is what we call as the momentum rate transform. And actually in this case, what we have is a sum of momentum rate transforms, and that sum comes because of the following. So this E1 here is 1, 0, 0, 0, and this ER is x prime by mod x prime. That is, it's a unit vector. So remember, I had the cylinder. So on the base space, it's a unit vector. So I have E1 plus IER. Now this I also plays a role. So I can essentially split out the odd part, the even parts, and because of this multiplication, so what I have is a sum of momentum rate transforms. Let me just, yes. So here is what I have. So I'm skipping a few steps, but if you believe me, this W here is the difference of the two corresponding to A and A tilde, and so then what I have is, so this multiplied by this and then multiplied by a weight. Now this weight I can choose, right? That is the power of this weight I can choose, and that is what actually helps us in actually solving this inverse problem. Now, why is it that I have a sum of momentum rate transforms? That is sum of a function momentum plus a sum of a vector field with an I plus sum of a two tensor field with the I square and I cube, etc. And that's because of this particular form. This E1 here is 1 zeros and ER is x prime by mod x prime. Okay, so the reason why we get this sum of this weighted integral transforms is because corresponding to E1. So if I just consider for the case of a two tensor field for simplicity, then I have E1 multiplied by E1, and that corresponds to the function part. Then I have E1 corresponding to the x prime by mod x prime part, that corresponds to the vector field part. And the third part is when I have multiplied with x prime by mod x prime multiplied by that, so that corresponds to the symmetric two tensor field part. So what I have is essentially I have an integral transform or a weighted integral transform involving a function plus a vector field plus a two tensor field plus a three tensor field, etc. But these come with I square, etc. So I can split it up and then do some things. And but what I want to emphasize is that this was studied earlier. So so this leads to the notion of momentum rate transforms in the last 10 minutes that I have. Let me just give you in the simpler version what is it that we actually studied this independently, and then it so turned out that this had application in this polyharmonic setup. There is one more thing that I want to emphasize is that this particular setup here in solving this inverse problem, the fact that you have the sum of the function plus the vector field plus the two tensor fields, etc., of the momentum rate transform, that is an added complication. The other thing is that you have only restricted to the unit sphere. That is, my C, which is x prime by mod x prime, is always a unit vector. Now, I cannot use any homogeneity properties corresponding to rate transforms here because I have different ordered tensor fields. So one implication is that because you're only restricted to the unit sphere, the momentum rate transforms will have a infinite dimensional kernel. But the usual momentum rate transforms, as I will show you, they will not have a kernel. So this is an added complication in this particular setup, but this can be done. Okay, so what is momentum rate transform? So let me just give you what is the rate transform. So the rate transform is this. The rate transform of a symmetric M tensor field. So what is a symmetric M tensor field? So it's a tensor field in which we permute any of the indices, the value is the same. Okay, so then the rate transform is given by this. And one disadvantage that of working with rate transforms is that it has an infinite dimensional kernel as soon as you go to vector fields and higher. Right? For the vector fields, it's quite easy to see. So suppose f is a vector field. Then you take gradient of any CC infinity function. That's again a vector field. Now you integrate along any way because phi is 0 at the boundary. It's going to be equal to 0. So the rate transforms as vector fields and anything higher by the same argument will have an infinite dimensional kernel. So therefore, from the rate transform information alone, you cannot recover the entire tensor. But for our polyharmonic inverse problem, our goal was to recover the entire tensor. Okay, so that's where these momentum rate transforms come in. So the rate transforms, this is the usual stuff. It has several applications. For instance, computerized tomography, it makes an appearance. Doppler tomography for the case of vector fields. So this is for detecting cancer using blood flow measurements, because the idea is that near the cancerous region, the blood flow is higher because there's more activity. And symmetric 2 tensor fields that come up in travel time tomography, or a linearized version of the travel time tomography problem. That is to map the interior of the Earth from seismic activity, seismic measurements. And 4 comes up in elasticity and things like that. So anyway, there are several very, very big shots who have worked in this field. Okay, so the kernel of the rate transform, as I told you, is an infinite dimensional kernel. So therefore, this is actually a result due to Sharafutdinov that you can recover, that you can decompose uniquely any symmetric M tensor field to the so-called solenoidal part plus the potential part. And the potential part is the dV there. That always lies in the kernel because V has a nice decay condition at infinity. Okay. Now this is the same as the Hodge decomposition. For the case of vector field, there is that decomposition. I think it's a Hodge decomposition. I forgot the name. There's a decomposition. The curl-free part plus the divergence part. Okay. So the D here is the symmetrized covariant derivative. You're working in the setting of a Riemannian manifold setup, or I call this as the inner derivative. So it is a symmetrized derivative because you need a symmetric tensor field, and delta is the divergence. Divergence along, you fix an index and then you just sum it up along that particular index, and it doesn't matter which index you choose because your F is symmetric. Okay, so there is actually an explicit inversion formula recovering the solenoidal part from the rate transform. Okay, so this is I'm not going to get into that the inversion formula. The inversion formula is quite complicated, involving fractional Laplacian. We'll actually see for the special case of function, which is what we are interested in. So now the question is this: natural question is, if you have, so we know that we cannot recover the entire tensor field from rate transform information. So the question is, what extra information would actually give you the recovery of the entire tensor? Okay, so one added information is this momentum rate transforms, in which you also have additional powers of this field. So remember, this was that R in the polyharmonic setup. So here it is the powers of P. So so the uniqueness question was actually done by Sharafutdinov. So what he showed is that if you give me I0F up to IMF, or in other words, K is equal to 0, K is equal to 1, up to K is equal to M, then F can be recovered uniquely, but there is also an inversion formula. And in the setting of real analytic Riemannian manifolds, this was done in a paper by Anuj Abhishek and Rohit Kumar Mishra. They use analytic microlocal analysis to actually show that. So they actually prove a Helgason-type support theorem in the setting of Riemannian manifolds. But what we are interested in, or what we were interested in at the time, was to recover, give an explicit reconstruction formula recovering F from the first M+1 moments. Okay, so these as I told you in the polyharmonic setup, we have this you know the data that is or you know from the data what you actually recover or what you show is that the sum a momentum rate transform involving a function plus a vector field plus a two tensor field etc. That's equal to 0, right? And as I told you that is an added difficulty because each of it has different homogeneity properties, and that is what is reflected over here. They have different homogeneity properties because you see that this jk here is the extended operator in which this x and the direction can be any point in Rn and c can be any point in R, any vector in Rn minus 0, and depending on what what k that you choose, it will have different homogeneity properties. That is a difficulty here. And so finally what we show is the following, is that we actually have a reconstruction formula, and the reconstruction formula is actually quite simple. What we actually do is we work with the extended operators which are given by jk. The jk's are given by as follows. So yeah, I can explain it over here. So this jk's here, so the I corresponds to when when c is the unit vector and my x is in the plane which is perpendicular to c. So this sometimes we call this as the tangent bundle to the unit sphere. But now I can naturally extend this for any point. So it's obvious, right? Because you give me a direction c and you specify a point, then there is a line that passes through that, or the unique line that passes through that point in that particular direction. But the integral, I can just shift this x. As long as I vary this x over this line, it doesn't matter. So what you do is you specify the x so that x lies in the plane which is perpendicular to c. So this is the tangent bundle to the unit sphere. But I can extend this naturally, the ray transform naturally for any point. You give me any point, any direction, using the homogeneity and using this translation, I can actually specify. So it's going to be the same information. So the advantage here is that if you're going to specify, if you're going to work with Tsn minus 1, then you do not have access to all derivatives, right? Because once you specify the c, your x is going to be in the plane which is perpendicular. So you only have access to derivatives which are tangential to this plane, right? But if I want to differentiate in all directions, then I can use the extended operator. That's the advantage. Or in other words, I can consider these derivatives. So once you observe this, then the point is that this I0 to Im and this J0 to Jm, these are equivalent information. That is, you give me this, I can get this. You give me that, then this is actually trivial because I just need to restrict. That is, you give me this is trivial. You give me these, then I can get this through this. Okay, it's not difficult. It just uses the homogeneity properties. Okay, so let me not. I do not have time to do this Fourier transform, but let me just tell you what is the inversion formula. The inversion formula is actually quite simple. You know, the thing is, you just need to take certain derivatives in x, certain derivatives in c, and then combine them. And that's what we show over here. So certain derivatives in x, certain derivatives in c, certain derivatives in x. This jk here is the kth momentum, extended kth momentum ray transform. And what you have done is that in that process, you have recovered the ray transform of each component of the tensor. So that now that is the ray transform of a function. And once you have recovered the ray transform of a function, then you actually have something nice, and you have a nice inversion form. You have a nice inversion form. So the inversion formula is essentially, so I is known. I is the ray transform of a function, and the integral over Sn minus 1 is it's like taking the adjoint, the L2 adjoint. So I have the L2 adjoint, and then you compose that with the fractional Laplacian and up to a constant. That's going to be your f(x). So in our in our polyharmonic, we don't need the inversion formula, but as I told you, this was the work on momentum actually preceded the work on the polyharmonic work. It's just that we just found that application recently. So that's the inversion formula. So we don't need the inversion formula for the polyharmonic work. We only show uniqueness. So that's all I have. So thank you very much for your attention.
Are there any questions from the audience?
Yeah, Shrikar has a question.
So ray is a convex object, right? Instead of the ray, convex objects
Yeah, so the question is, are there other objects on which you can integrate and recover the function? So yes, of course, circular radon transform. So all these fall into this umbrella of what we call as generalized radon transforms. So circular radon transforms comes up in ultrasound reflection tomography. Spherical radon transforms, they come up in thermoacoustic tomography. Then there are several. Okay, geodesic ray transform, which if you consider so this was Euclidean setup, but you can also consider in a Riemannian manifold setup, then the shortest length curves will be geodesic. So you can consider geodesic ray transform. And you can also consider radon transform, which is integral over hyperplanes. And that was originally radon actually studied this for the context of wave equation.
each of these cases there is an inherent geometry which is very much useful.
Correct.
All of them are basically they have an inherent geometry which is very general convex.
So the question is, what Shrikar is asking is, what about general convex sets? Yeah. Okay. So my knowledge is only limited to this, in the sense that there is an application.
If I take a convex set, and I look at various locations or shifts of this convex set, and I look at the intersection of this convex set with the subject of over these intersections.
Okay, but this is not a one-dimensional. It's not a one-dimensional integral anymore, right? Okay. For the case of D planes, it has been studied, right? But I do not know for. Okay, your question is about what if you take a ball, then you intersect it, and then now you have a lower dimensional set or something like that, and then you, yeah, that I don't know, or at least I have not, I have not gone into that part. Yeah.
Then the thing is that you look at the more generalized paper. Then when you take the inversion, that's how it really
Yeah. So
it is like
no.
It is like inversion of variable coefficient.
Yeah. So the question is, what if you consider variable coefficient in the principal order term but known? Correct. See, the difficulty is the ansatz.
But I think the inversion also has a different difficulty because it's no longer simple differential. More general Fourier.
That is true. But even before you get to that integral identity, proposing an ansatz is difficult. It's not known. So, for instance, what is known is the following: if you have one direction to be Euclidean, but the base. So what we did is we split it up into a base. So the base can be, for instance, a Riemannian manifold, but one direction is Euclidean. Then I can still specify the limiting Carleman weight, which is linear in that particular direction. Then what I would end up with is, instead of the ray transform, I would end up with momentum. Okay, we expect momentum ray transforms along geodesics on the base manifold. So then, at least for real analytic category, maybe there is hope for a uniqueness system. But at least
some support here.
yeah. So for the momentum, it was done, at least for real analytic, it was done by Anuj, Abhishek, and Rohit Kumar Mishra.
But not when the symbols are
Not in this.
and like not when the symbols are T of X.
Yes, not in the general set. Not in the general.
Not when the principal symbol is T of X.
Yes. So one direction has to be still Euclid, but they did not consider a Calderon problem. They just studied an integral geometry problem. But the general case, the difficulty is proposing an ansatz, a proper ansatz. Or the notion of limiting Carleman weight itself. See, it's not enough just to produce a limiting Carleman weight. You also need to produce enough solutions to solve the inverse problem, and that's where the principal difficulty lies. Any questions? So at least from the audience here, there doesn't seem to be.
Are there other questions from the audience, from the virtual audience? In this case, let's thank the speaker again. Let's thank Venky again.
Yeah, thank you, Nishant. Thanks, everyone.
See you.